Woohoo! Welcome back. Tonight we're going to be working with dum dum dum, the area under the curve. Woohoo! And we're going to start off with a problem. How can we calculate the area under a given function, which is really the area between a function and the x-axis? And I've drawn a little picture here. So if f of x is this little curvy bit, then it's everything between it and the x-axis. So it's this little wiggly piece. And we go on to think about it. If the graph happens to be something easy, like a horizontal line, it's pretty easy to do it using geometry. But if it's curvy like this, the problem becomes more difficult. Now, this is coming out of nowhere. So I'm going to ask you for suspension of disbelief that this technique is going to lead us to a big part of calculus. In fact, the second half of calculus. And unfortunately, because this particular class does not go deep, we're just all going to have to agree that this is a very important problem, even if you're not quite sure why. So at the end of this section, we'll have some word problems that will hopefully help us see what's going on and why it's a useful question. But just for now, we're going to say, this is what we want to do, and let's see how to solve this interesting problem. So we've got a graph. So here's our function right there. The f of x part, the part that is f of x is just this piece right here. It's just that. That's the curve. We're going between x equals a and x equals b, and we want to know the area here that we're labeling S, that whole area. We want to find out what that area is. And because this isn't a rectangle or a circle or a triangle, we don't have a formula that tells us what this area is. So this is the problem we're starting out the section with. And what I'm going to propose is a very classical solution, which is we take a look at this and we say, you know what? I'm going to say I've got here, right here, this is f of a. This is the y value at a. Here's f of a. And I'm just going to draw a rectangle. And then my rectangle is f of a high. And then across, this is the difference between b and a. So it's b minus a. So I've got a rectangle that is f of a tall and b minus a wide. So the area, which is equal to the width or the length or the height times the other one, is going to be f of a times b minus a. So there's my area. Now, this is an estimate. And we can tell that with this particular function, this is way too big, right? Because if I look at this whole estimate here for this rectangle, I'm including a bunch of stuff that isn't in the orange part, which is what I really want. So this is way overkill, right? Now, notice that I could have used f of b, and I could have gone across here and just looked at this little rectangle, and that would have been an underestimate. So, and that's what the note is down here. We'd get a different estimate if we used f of b instead. So, in fact, I could write out, although I don't need to, but I could write out that our actual estimate, the f of a times the difference between b and a, is bigger than our actual area that we're looking for, which would also be bigger than f of b times b minus a, which is just interesting to note. So I've got, this little rectangle here that I also could use as an estimate. Now, we can all agree, though, that even though this gives us kind of an estimate, a way to sneak up on S, these are terrible estimates. They're completely wrong, right? The big one using f of a has way too much extra that shouldn't be there. And f of b is missing, it's only getting like half of s or 2/3 of s. So we're missing a bunch of stuff there. Not great estimates, but this is where we start with mathematics, is we start with estimates and see if we can make them better. So, next page, let's see if we can make it better. How do we get a better estimate? And here, we're going to try 2 rectangles. So, what I'm going to do is I'm going to go halfway between A and B, and I'm going to roughly mark it, and that's going to be the point C. And then I have, here's the point f of a, right? This is f of a up. The full point is a comma f of a. And then I can also go up to C. There's FC, f of C. And so instead of just going across with one big rectangle, what if I broke it down into 2 different parts? And so I did this rectangle here. So I did this area. I'll mark this in green. I'll do that area. And then I'm going to do another rectangle. Wow. I should be using a ruler. Sorry about that. And this one I'm going to draw in. Can you see the yellow? It kind of shows up a little bit. So I've got 2 rectangles. I've got the green rectangle. And I've got the yellow rectangle. And that gives me my new estimate. So the area here that I am hoping it's going to be close to the green rectangle plus the yellow rectangle. Now, here, let's see, I've got f of a, that's my height, times, and here I'm not going all the way from A to B, I'm just going from A to C. So this is C minus A plus, and then this height, it's not all the way to f of A, it's f of C times B minus C. Okay, so this is all very formal, and this is what mathematics looks like sometimes. It's very formal, a lot of details. But then we're going to say a couple of things. We're going to say, if I pick C carefully, then I can choose it so that the distance from A to C and the distance from C to B is equal, right? I could pick C right in the middle. So that would be an interesting way to go. And I can also, rather than worrying about C minus A and B minus C and all that, what I can do is I can bring in a Greek letter, and the Greek letter is delta. And so I'm going to say this distance is delta x2. And I'm going to say this is delta x1. Delta is a Greek letter, and we use it to mean change or difference. So this means how much did x change here? So what's the width here? How much did x change here? What's the width there? And so we can rewrite it as f of a times delta x1 and f of c times delta x2. So that's the area of 2 rectangles. And then we have some language we're going to use. The language is, we say that we are calculating the area. Okay, we're going to estimate it with left endpoints. Remember, left is that one. So left endpoints over 2 sub-intervals. There are 2 rectangles, so we're breaking it down into 2 parts. So the question, same question on every page. How do we do better? And have we done better? And I'm going to say, I think we actually did improve our estimate a little bit. There's more work because instead of just doing one big rectangle, we're going to actually work out 2 areas, which is going to take twice as much time. But here, my overestimate is still, that's still pretty big, but I didn't continue it all the way. And if we look at the yellow one, we missed this little piece right here, but we got a little bit extra there. So I think the yellow rectangle is actually probably pretty close for this part. So I think we've got a better estimate. So I do think we've improved things. And given that, what can we do to make it even better? And here's going to be the problem in math. In general, if you want a better estimate, you're gonna have to put more work into it. So there's gonna be a trade-off. If you want it quick, what was quick? Quick is one rectangle, you just do it, and it's a terrible estimate, but you're done. Better estimate, 2 rectangles. Still not great, but better, but twice as much work. And you can kind of guess what's going to happen next. What's going to happen next? Dun, dun, dun! And I know this escalated so quickly. So we're going to change the problem. And this is going to allow us, rather than me just waving my arms around and my hands around, we're going to actually look at very specific values. So we've got a problem that says estimate the area under the curve f of x equals x squared. So we know x squared. We've played with it. This is a parabola. We want just between x equals 0 and x equals 1. So I've got graphs. And take a look at those 2 graphs. The red line right here, I don't have a really great red highlighter right now, but let me draw this. This is y equals x squared in both cases. Ooh, I'm tracing pretty well. Look at these amazing powers of tracing. So the red line is the x squared, y equals x squared. And we're going to divide the interval between 0 and 1 into 8 subintervals. Super fun, right? So how many rectangles are we going to do? We're going to look at 8 different rectangles. Okay, that's going to be a lot of work, but is it going to get us pretty close? And I would claim that with 8 of these little boxes, now let's take a look. Here, we've got boxes that stay under the line, so our estimate is going to be too small. And here we've got boxes that are over the line, so this estimate will be too big. So this is going to be an overestimate, and this is going to be an underestimate. Can you see that? That if we actually want the area under the curve, this is missing, right? This is missing all of this space. This space is missing. So our areas are not quite big enough because we're missing all that space. But over here, we're getting too much, right? This stuff is sticking out. We don't really want to count this. So all of this in here, this is too much. Between the 2 of them, what we're hoping to do is to come up with a good estimate. So, why is this using left endpoints and why is this using right endpoints? So let's take a look at these different points. So this is 0 to 1. We're going to break it up into 8 subintervals, so each one is 1/8. So this is 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and then 1, which is 8/8, right? So if we look at 6/8, this is what happens when we're at 6/8. So we draw the rectangle across. And so this one rectangle right here, if I just pick this one, I just picked it at random. This one right here, I'm going to draw it over here so we got a little bit of space. This is going to be 1/8 across, right? We broke it up into 8 subintervals. And then here it's going to be f of, and it's f of 6/8. And we find the area by multiplying those two. And so we're going to have to calculate each of these areas. Okay, are you guys ready? Woohoo. So the good news is that in the next couple sections, we're going to take this to the next level, and we're not going to have to do these details anymore, but we're going to start with these details until we get good at them. So let's go ahead. We're going to go ahead and do the left endpoints. So my points are going to be from the left. I'm going to do f of 0 times 1/8, right? That's that first box. Plus f of 1/8 times 1/8. Now, why am I multiplying by 1/8? That's the width, right? That's the width of each one. Plus f of 2/8 times 1/8. Plus f of 3/8 times 1/8. Plus f of 4/8 times 1/8. Plus, we're almost there, f of 5/8 times 1/8. Plus f of 6/8 times 1/8. Plus f of 7/8 times 1/8. Now, let's take a look. Box 1, box 2, box 3, box 4, box 5, 6, 7, and 8. Now, why don't I have to do 8/8? 8/8 or 1 is on the right-hand side, so I'm not going to do that. Okay, so far so good. What is my function again? My function is x squared. Okay, so those of you who love fractions, I know, you're having a party. So the area is approximately equal to that. So what I'm going to do, f of 0 is 0 squared times 1/8. Plus f of 1/8 is 1/8 squared times 1/8. F of 2/8, 2/8 squared times 1/8. 3/8, 3/8 squared times 1/8. 4/8 squared times 1/8. I'm going to run into mine, so I'm going to start heading downwards. 5/8 squared times 1/8. 6/8 squared times 1/8. Plus 7/8 squared times 1/8. So sometimes I think the best way to develop new techniques in math is to have to do something really nasty like this so that you really dislike it, so that you think there's got to be a better way. And there really is a better way. But let's go ahead and finish this one. The good news is 0 squared is 0. So this term is just 0. This one is going to be 1/8 times 1/8 times 1/8. So that's going to be 1 over 8 cubed. This is going to be 2 squared on top and 8 squared times 8. So this is going to be 4 over 8 cubed. This is going to be 3 squared times 1, so that's 9, all over 8 times 8 times 8, 8 cubed. And in the same way, we'll get 16 over 8 cubed. We will get 25 over 8 cubed. We will get 36 over 8 cubed. We will get 49 all over 8 cubed. Okay, so I've got a bunch of numbers here. And if I add them all together, first thing I need to know what 8 cubed is. 8 times 8 is 64 times 8 is 48504, I think. If you're wondering, why aren't you using your calculator? Well, the answer is I left my calculator way over there on the table. So I can't get to it. So it's 32. 6 times 8 is 48, 512. There we go. So we get 1 over 512 plus 4 over 512 plus 9, 512 plus 16 over 512 plus 25 over 512. I know this must be as exciting as watching paint dry, watching someone do long calculations on YouTube. I know, but this is how you become a YouTube star. That's what I've been told. Okay, so we've got all of these. And again, sadly, no calculator. So let me see if I can get this. This is going to be 50. These two are together going to be 40, so that's 90. This is 115, 124, 134, 140, I believe. So what I'm going to do is, since we've gotten to 21 minutes at this moment, I'm going to go ahead and I'm going to stop this video now. We will continue. And in the interim, I will go and grab that calculator over there, which is very exciting. I know, I'm a tool-using mammal, and I'm very excited about that. And we will come back, and I know you guys are going to be waiting with bated breath, because did I do the math correctly? I don't know. We will find out. So go get a snack, go get something to drink, take a rest, go look outside, pet some animals, hug some trees. Know that you're amazing and incredible and so smart, and I'm so impressed by everyone who's taking this class, honestly. And if you've made it to this point in the video, I'm very impressed if you have not fallen asleep. So I'm going to quickly end the video, and then I will come back with exciting calculator action. And until then, woohoo and math on.